Welcome to section 12.2, Test for Independence and the Homogeneity of Proportions. We're just going to be focusing on the test for independence because the homogeneity of proportions is not required for this course, so we're not going to go over it. But we are going to go over the test for independence, and it's the independence of variables, and we're going back to our Chapter 5 definition. That means that the probabilities are not affected. And we're going to look at the test for independence of variables when they're organized in a contingency table. So the test for independence is used to determine whether there is an association between a row variable and a column variable in a contingency table constructed from our sample data. Our null hypothesis is always going to be the same. The null hypothesis is that the variables are independent. And the alternative is that the variables are dependent. So let's look at an example. So suppose a sociologist wishes to see whether the number of years a college person has completed is related to his or her place of residence. A sample of 88 people selected and classified as shown. At the alpha equals 0.05 level of significance, that tells us we're doing a hypothesis test. Can the sociologist conclude that a person's location is dependent on the number of years of college? All right, so again, some key words. Alpha tells us it's a hypothesis test, and we want to know if our variables are dependent or independent, something like that. And this is the data we have. Okay, so our approach is these are the actual counts, the observations. We're going to compare the actual counts from the sample so like the observations we're going to throw in a vocabulary word here, expected counts. And the expected counts are assuming are the values they would be if they are actually independent. So let's see how we're going to get the expected counts. Okay, so if we recall from our Chapter 5 lecture notes, that variables are independent if the probabilities don't affect each other. And we also had a numerical way to calculate that as follows. So variables are independent. I'm going to abbreviate that, independent. One way that we tested for that was the probability of f given E is just equal to the probability of f if our variables are independent. And the other thing we know, and the one that we're going to use, that the probability of E and F, our multiplication rule for independent events, is just the probability of E times the probability of F. And that's what we're going to use to get the expected counts. So the expected value of a cell, F and E, let's write this out, all right, so the expected value of a cell E and F would be the probability of E and F times the grand total, or the amount in the sample. All right, it's a percentage. Probability would end up being a percentage of the grand total. All right, this is how we're going to calculate the expected value of a cell. Let's clean this up a little bit, of course. Okay, so probability of E, we're going to count up. So let's go back up and look at a specific example. So let's say our E and F is no college in an urban location. All right, so here's our event E. It's living in an urban area. Here's our event F, no college. 15 is E and F. Okay, so probability of E, probability of living urban, we're going to have to add up this row total and then divide it by the entire total. Likewise, the probability in the sample that people don't have any college, we're going to look at the row total and then divide by the total amount in the sample. So that would look like this. So probability of E, it's row total over grand total probability of F is column total over grand total amount in the sample. And then that's going to be a percentage of the grand total. So times grand total. And we can cancel some things. Grand total cancels out. And so we have then a formula for the expected value or the expected frequency of each cell. It's going to be row total times the column total over the grand total. Okay, so while we're here on this first page, let's go back up to our contingency table and let's add up all of our rows and our columns. All right, so if we do that, you can pause it and then come back and see what I have. We're just adding, though, straight across. So out of these 88 people, 35 live in the urban environment, 32 live in a suburban environment, and then 21 live in a rural environment. Out of the 88 people, 29 did not have college, 35 had a 4-year degree, and then 24 had an advanced degree. All right, there you go. Okay, so we know our approach. We're going to compare the actual counts to the expected counts. Now we know how to calculate the expected counts. So let's start running our hypothesis test. Again, this is called your chi-squared test for independence. The hypothesis is always the same, that the variables are independent for the null hypothesis. And the person's place of residence then is dependent on the number of college years for the alternative. And again, we're going to essentially construct our contingency table using the fact that the variables, or assuming the fact that the variables are independent. So our level of significance is given to us. And now we're going to calculate the expected frequencies for each cell. And again, this is assuming the null is true. So it's the same format as all of our other hypothesis tests. Okay, and we just learned how to do our expected frequency. It's the row total times the column total over the grand total. So the expected counts, if we're assuming these variables are independent, people that live in the urban area and don't have any college degree, it should be 11.5. All right, and then we're just going to continue on our merry way. Row column, row total, column total, divided by grand total. All right, and I'm rounding these. That's fine. All right, so we're getting the general gist. I'll fill in the rest of the numbers instead of all the calculations, and we're ready to go. All right, so again, we're going to be comparing these expected values with the actual observations from our sample. Our assumptions to run the hypothesis test we do after we do the expected frequencies. And our assumptions for this hypothesis test is all expected frequencies, so what we just calculated, are greater than or equal to 1 and no more than 5% of the expected frequencies are less than 5. Whoops, excuse me, not 5%, 20%. All right, and notice in our case, our lowest value is 5.7, so we're good to go. If we ever had this case, we can always combine classes or combine variables, or we could look at a larger sample size until we meet our assumptions. All right, next is our test statistic. So we're going to see if this test statistic is unusual considering our null hypothesis. So really similar to what we were looking at before, it's all our observations minus the expected values squared divided by the expected values. And this test statistic, again, like section 12.1, it's on our chi-squared distribution. And our degrees of freedom is the amount of row variables minus 1 times the amount of column variables minus 1. All right, so in our situation, we had 3 row variables, 3 column variables. So 3 minus 1 times 3 minus 1. 2 times 2 is 4 degrees of freedom. But let's do all of our calculations together. Okay, so our test statistic, so notice we have to go through and do this 9 times. We'll just kind of do the expedited version of this. That first cell, the observation, is 15, and the expected value is 11.5. So we're going to square that and divide by the expected value. We're going to do that 7 more times. So a little bit of teacher magic right now. And then that last cell, the expected value, or the observed value is 7, expected is 5.7, and divide that by the expected. And if you add all that up, our test statistic is 3.01. So again, we would have to do that 9 times, a little tedious. And like we were talking about before, our degrees of freedom is 4, because there's 3 row variables, 3 column variables. All right, so now let's go to our chi-squared distribution. And we're going to see if our test statistic 3.01 is unusual using the classical approach or the p-value approach. So let's remind ourselves of a couple things. Our test statistic is 3.01, our alpha is 0.05, and then our degrees of freedom is 4. So let's look down at the classical approach. Here is our chi-squared distribution. We again are going to compare the critical value chi-squared sub alpha to our test statistic. We can find our critical value using our chi-squared distribution. It's organized just like our t-distribution. So you would go chi-squared of 0.05 with 4 degrees of freedom is equal to 9.488. So this value right here is 9.488. That's our chi-squared distribution. So we can see that our test statistic, which is 3.01, is definitely not in our critical region. It's in the OK zone. So not in critical region. Okay, so we're not going to reject the null hypothesis. Let's look at the p-value approach. So the p-value approach, we're going to the right of our test statistic, which is 3.01. So go to second vars, the distribution, and get your chi-squared CDF. Lower bound, upper bound, degrees of freedom. And you would get 0.556 via calculator, which again is bigger than your alpha. So again, we know we're not in the critical region. We're not going to reject the null. Again, this is telling us our test statistic is not considered unusual. It is A-OK. So we're going to keep our assumption that the null hypothesis is true. State our conclusion. Okay, so same as before. What kind of evidence do we have? We have insufficient evidence to support the alternative. At the alpha equals 0.05 level of significance to conclude the alternative statement, which that the variables are dependent. So that a person's location is dependent on the number of years of college. And there you go. Okay, so that's the nitty-gritty. We're going to be looking at an example now, example 2, which is going to look more like what you guys are going to be doing on a quiz or an exam. And our calculator function is a little bit more complicated than our other calculator functions, so we're going to switch over to our computer screen video, and we're going to finish out that section there.